This is Lab 6 for Physics 2212, Magnetic Molasses. The purpose of this lab was to observe magnetic induction of currents by analyzing a bar magnet falling through an aluminum foil tube. We also compared the observed model with a computational model in GlowScript. The system was the tube and the magnet, and the surroundings were everything else. And as a preview of our results, the experimental time was 1.254 seconds, and our computational time was 0.861 seconds. Important theory for this lab includes the Biot-Savart law, which describes that magnetic field is produced by a current-carrying wire depending on current, distance, and orientation, which can be seen at the top, and Faraday's law, which describes a change in magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux, and an induced voltage that opposes the change in flux. And Newton's second and third laws, which state that net force is equal to a change in momentum over time, and that every action has its equal and opposite reaction. The experimental procedure for this lab was to drop a magnet into an aluminum tube and record time, but we noticed that the fall time was significantly slower than what you would expect, and this was due to an upwards magnetic force from induced currents. We've repeated this procedure as necessary, and to the right you can see a little diagram. We made the assumptions that there was negligible air resistance, the bar magnet was acting as a dipole, and the system only contained magnetic and gravitational forces. From our experimental procedure, we have our different trials and the different times that we recorded. The tube dimensions were a length of 0.3 meters, width of 0.6 meters, inner radius of 0.026 meters, and outer radius of 0.032 meters. The magnet had a mass of 0.025 kilograms and a dipole moment of 1.613, and the average time for the magnet to fall through the tube was 1.254 seconds. We then used those observed quantities to input into our initial conditions for our computational model. So we have physical constants such as the resistivity of the aluminum, gravity. Here we created the tube with those measurements, and then we also created the magnet with the mass and the dipole moment. And then we also inputted those same values to help create the flux and the magnetic field for the bar magnet. The major chunk of the code was dedicated to creating all the forces that act on the magnet, which would be the downward gravity and upward magnetic force. So here we can see that we're calculating that magnetic force from the tube on the magnet, as well as the gravitational force before. And in the end, we'll calculate the net force by adding together our F-grav and F-magnetic that we calculated earlier, which will in turn give us a graph that we'll see on the next page. These were the results of the computational model, including a little diagram with two different colors representing two different currents. We will talk about the directions of these currents in a little bit. But this is the graph of velocity versus time that this computational model generated. You can see in this first section it's very steep, and from this we can determine that the force of gravity is greater than the force from the magnet, which means that the magnet is accelerating. And, well, the majority of the time spent in the tube, we have a flat line which says that our gravitational and magnetic forces are equal. And in this third section again, we have the acceleration, meaning that once again, gravity is stronger than the magnetic force. Here were some questions for our observations given to us in our instructions. First question is, what color corresponds to clockwise or counterclockwise? And by using Lenz's law, we can determine that red is counterclockwise and blue is clockwise. What happens if you flip the magnet? The magnet would still fall the same way, but the current directions would be flipped. How does real-world time compare to computational time? Computational time is slightly shorter, most likely due to resistance in the real-world scenario. What does the plot shape tell you about the forces acting on the magnet? It tells us that gravitational force is greater when the magnet enters and exits the tube, but equal in the tube. Sources of error could have been friction, errors in time measurements, and air resistance. What if the resistivity of the conductor was reduced as close as possible to zero? Well, this would mean that the induced current would be greater, by Ohm's law, therefore creating a stronger opposing magnetic field and a slower magnet ball time. And what if we cut holes or slots into the tube? Well, this would mean that there would be less places for current rings to be induced overall, so the opposing magnetic field would be weaker and the magnet would fall faster.